meant to be recording this. Should I record it?
I am, it's fun.
Okay.
It's going to be good quality.
So here are some of the topics we're going to cover today. Some of you might already be familiar with some of these. Actually, can I just check the audience in the room? Has anyone studied data structures before? A few people. That's good. Has anyone studied algorithms before? The same sword in hand. Okay, cool. Well, I'll assume no knowledge, which I think is probably the fairest way to go. Also, I can't cover all of data structures, but we'll just do a small selection to give you a taster of what learning it is like. So I wanted to point out at the beginning that you won't have learned data structures, learned data structures by watching this talk. The best way to learn any technical topic, including data structures, is unfortunately, or fortunately for some, dedicated self-study, just spending a lot of time with it, looking through lots of examples. Nice to have is a mentor who knows more than you to check your answers and point out where you're going wrong. I taught myself to code, before going to a boot camp, but at the beginning I was teaching myself to code. And if you don't have a mentor, then you can also use the internet. There are sites to sort of check whether you're getting things right or wrong. But that's how we go. So here are some questions I thought might frame the topic a little bit. So it is true that you usually teach data structures alongside algorithms. You're probably interested in algorithms too. If you are, look out for my upcoming talk, Algorithms 101, which I will do if this goes well and I don't break something and spontaneously burst into flames. I think there is a case to do data structures first before algorithms, partly because algorithms need to operate on data. So to me, it makes sense to look at data structures first before the thing that operates on them. But most courses and books that cover this often just have algorithms in the title, so look out for that if you're looking for learning resources. I wanted to include this. So Linchuan Zhang, or Lynch for short, is an interesting friend of mine. He's interesting partly because he's in the effective altruism community with me, except based in San Francisco. But he's mainly interesting because he taught himself to code. He doesn't have a math background or technical background beyond school, really, and successfully got a job at Google that way. The story is quite interesting and it involves a lot of coding competitions. I can give you more detail if you're interested. But he basically wrote down some advice for some friends, which I'm not really meant to share, but here's some of it anyway. The most important thing, I think, is this middle point. If you haven't heard of the algorithm before, but know the underlying data structure, you can often derive a good enough algorithm for the task. The reverse, however, is frequently not true. So, to me, that seems like quite a good case, like a very compelling case to learn data structures before algorithms. He also recommends me a number of books, including the Algorithm Design Manual, on which much of this talk is based, but I'll explain that more a bit later. Right. I think it's important to grasp how data structures fits into computer science learning more generally. This is a short and funny video that I've watched many, many times, but I think does a great job of explaining computer science as one connected thing, rather than just a range of different unconnected concepts. I should apologize first for how American he is. Actually, I think he might be Canadian. There are a lot of you guys, and he says the word bud a lot. But hopefully, if you're able to see past that, there's a lot of cool stuff here, especially once we get down to the level of circuits and electricity. So, strap yourself in. I hope the sound works. Let's have a go.
I just want to show you
Alright, let's start it down a bit.
how Buckley's. We're going to see how well my brain can operate with sneeze. Yep, no, this is not going to be a good video. All you need to know is that we have variables, we have conditional statements to do different things based on these variables, we have functions, we have the ASCII table to represent characters with numbers, and we have arrays, which can store multiple variables. So we can reuse this one object to store data about every family. We can create an individual of a husband and a wife. This is the thing, is that you can put objects inside of other objects. Once you feel comfortable with using data structures, this is where your coding life gets interesting. In the C language, you gotta do everything yourself, bud. Let's get a basic program going here. So it's something like GCC test.c. By the way, C was actually written in like the 1970s. Allocate memory with a size of int times 3. We've created a pointer. If we want to access this block, all we have to do is we have to say pointer plus 1, or pointer plus 2, pointer plus 3. Dereference num plus 2. This and this are the exact same thing. Num2 to num plus 2. Every other language is built on top of this. So once you understand how C works, you can do everything. I never read books, yo. If you guys are asking me for a book, this is the only book I can recommend. Here's a list structure, which contains a function pointer, a pointer to a function. So it's kind of the same as an object in Java. We have variables and we have functions. It's at a lower level now. Insert back. Oh yeah, and then I had to do, look, if list head equals null, if list head equals null. In C, strings do not exist. You create an array of characters, and we're going to call it string. Size of char times 10. The last character is a \0, right? Ah, look, hello, it's there. Nobody actually sets their strings like this in C. strcpy. You type in hello, and it does the same thing. Okay, look at that. Hello. We have Java. Java is pretty high level. You break it down to C, you understand how C works, and then now you've got to write assembly, and assembly can run on a chip. I'm going to code this in assembly. See if I remember exactly how to do that. I love it. I love it. I just realized, in order to understand this, you need to understand hexadecimal. So we have 16 numbers in hexadecimal between 0 and 15. So F equals 15. It makes it easier for programmers to look at an F than to look at 1111. Look up binary to hexadecimal. This is our memory. We put 15 into byte 9000, so you can see 0F. And you can look at 6, which is in 9001. Shouldn't it have placed it there? Check the stack pointer. And yes, awesome. So we put 15 onto the stack. We put 6 onto the stack. When we execute jump to subroutine, it's going to push the address of the next instruction. So if we look on the left here, 8012. That's going to fill these F's right here. Hey, bud. This is the assembly equivalent of some num function, pushing x onto the stack, pushing y onto the stack. This is the preparation for calling the function. Whereas in C, you don't have to do that because you just call a function. In order to access the variables in memory, we could just put x here, but the whole point is when you call a function, it creates a local variable. So in order to create a local variable, that's the equivalent of pushing something onto the stack. That's why we have to prepare them, call a function. Once we get into the function, we move the value of x into a register, add y onto D0, return from the function, save it to memory. I'm going to read what I wrote, and you guys may not understand it, but I think it is hilarious, okay? How does a computer do addition? That's your next question of low level. Engineers discovered that they can make an adder circuit super fast. They practically perfected the adder circuit. They obviously want to reuse the circuit for as many operations as possible. A minus B is the same as A plus negative B. So how do we represent B in a negative form? All you do is flip all the bits and add 1. So mathematicians discovered this, and they figured out, holy shit, this is going to revolutionize the whole world. 10 plus negative 6. B was 110, 2's complement, plus 1. So 6 in its 2's complement form is 0, 1, 0. Okay? We're going to add these two. 0, carry a 1, 1, 1. Whenever a number starts with 1, that means it is negative. we need to convert it back out of 2's complement form, and we end up with 0, 1, 0, 0, which is 4, which is 10 plus minus 6, which is 10 minus 6, which is 4. So you're looking at this and you're going, is this magic? Wait, you go, wait a second, and you realize that all of a sudden, mathematics is more interesting than you thought, because yo, when I get questions on my channel, people ask me, do I need a lot of math for computer science? Do I need to know a lot of math? And I go, no bro, all you need to know is addition. Every data structure is built on top of pointers, and pointers operate using addition and subtraction. Addition and subtraction is implemented through addition. So all we have is addition. And then if you want to go really deep, you can get into logic design and build your own adders, which, oh my god, I think I might be able to show you. So it's crazy just to get lower and lower. Oh my god, everything's making sense now. Like my whole life is shocked. A full adder involves 2 AND gates, OR gate, XOR, XOR, and then these gates are implemented using transistors. So yeah, I still don't know all that much about the transistor level, which is on my list of things to research. I'm not even sure if this video was like a good, I think I was supposed to tell you guys how to get started learning computer science, but I think I just went on this crazy rant and explained like the past 3 years of what I've learned. The main things is choose a language like Java or Python to start learning the basic constructs of if statements, functions, objects. Once you feel really comfortable with that, move to C, and then try to recreate your programs in C. And then once you feel comfortable with that, do some pointers in C, and then work on data structures, okay? Start with a linked list, go to like a stack, go to like a queue, look at some hash tables, trees, all the pointers, man, all the memory management, all the pointers, read the C programming book. Once you feel like you're so good at C, which that won't happen quick, okay? You know, you could go and work on some bigger applications, right? You can build pretty much whatever you want at that point. But what I would recommend is at least try assembly. Honestly, once you get to that point, you know, your life will be much easier. Because that's pretty much where I'm at, and I'm just like, I feel like I can just teach myself anything, you know?
I think that's enough for this guy. So hopefully some of that made sense. But after that quite hurried overview of computer science, I thought we should do some preliminaries before actually getting into data structures. The first thing to know about Big O notation is that it's about the worst case scenario. So if you see a lot of O's and you kind of don't really know, wait, but surely we can like benchmark codes if you want to know like how fast it runs. It's not about benchmarking, it's not the same. It's about capturing like orders of magnitude difference in code execution time. For the stuff that we're talking about, we're kind of looking at that bottom right. So O log n or O1 will be considered like good, and anything like ON or worse is just going to be too slow. But I've included all those up there just so you know there are like lots of different options. As a little aside, if you want an example of a really bad algorithm, so the worst one on there, if you look at the bottom left, is n factorial. Has anyone not come across factorial before? Okay, so the worst algorithm for the traveling salesman problem is just like manually checking every single pair, and it turns out that's just like a really bad way of doing it. But I don't want to get sidetracked, so let's move on. Hex and binary, I don't know whether people have come across hex or like hexadecimal before. I remember when I was like playing around when I was a teenager, there were these like websites that taught you how to code, and I remember there were these like hex and binary converters, and there was a website where like you had to like kind of follow these like clues and like solve this mystery. So I think I learned about like hex and binary converters like way too young. But if you didn't know